Hello everyone, I'm going to talk about the novel method for testing composite null hypotheses. We consider a hypothesis test. The null hypothesis is theta in the big theta 0. Alternative hypothesis is theta is in the big theta 1. Theta 0 and theta 1 are disjoint subsets of the parameter space theta. And little theta denotes the parameter for population distribution from which the sample is observed. A hypothesis is called a sample if it specifies little theta to be a single point. A hypothesis is called a composite if it is not simple. For simple versus composite hypothesis test, null hypothesis is little theta equal to a point little theta 0. Each alternative hypothesis, H1, is the little theta in a big theta 1. The likelihood ratio test rejects H null if and only if the likelihood ratio is less than or equal to a certain critical value, little c. For a predetermined significance level alpha, the critical value little c is the largest number satisfying the following inequality. If the null hypothesis is a composite, the likelihood ratio statistic is defined as lambda equals supremum of the likelihood for little theta in the big theta 0 over the supremum of the likelihood the little theta in the big theta 1. However, the distribution of lambda under the null hypothesis generally depends on the specific value of little theta in the big theta 0. The critical value little c for a given significance level alpha is often selected to be the largest number satisfying the following inequality. If dimension of big theta 0 is d0 and the big theta 1 has the dimension is d1, when d1 greater than d0, the distribution of the statistic minus 2 log lambda converge to the distribution of chi-square with the distribution with the degrees of freedom d1 minus d0 as n goes to infinity. The fact that this asymptotic result holds regardless of little theta 0 offers great simplification in constructing a testing procedure with approximate level alpha, where H null is rejected if minus 2 log lambda greater than the 1 minus alpha percentile of the distribution chi-square with degrees freedom d1 minus d0. For a finite sample size n, this approximate test has a bias in the sense that the actual significance level differs from the nominal significance level alpha. Developing an accurate finite sample test typically requires a closed-form expression for the likelihood ratio statistic lambda and a good understanding of its distribution under each point in the big theta 0, which is not available in many situations. And handling nuisance parameters in hypothesis testing has been a long-standing challenge in statistical inference. Although previous work by Besu, Reed, and Fraser, and Royal have significantly advanced the field, challenges remain, particularly when dealing with finite samples or complex nuisance parameter structures. Our work aims to complement these existing approaches by offering a robust framework for testing composite null hypotheses and constructing confidence intervals that remain accuracy in finite samples without requiring auxiliary statistics or asymptotic approximations. So we consider a new method for the hypothesis test H null theta in the big theta 0 versus H1 theta in the big theta 1. So given a sample X, the composite null hypothesis H0 is rejected if and only if the simple null hypothesis theta equal to little theta 0 is rejected at level alpha prime in favor of the H1 theta in the big theta 1 for every theta 0 in the big theta 0. In other words, the H null is rejected if and only if this following inequality satisfied for every little theta 0 in the big theta 0. How to decide the alpha prime? So let the C prime alpha prime, depending on theta zero, be the critical value for the simple versus composite likelihood ratio test statistic satisfying this equation. Then the critical region for the composite versus composite hypothesis test H null, theta in the big theta 0, H1, theta in the big theta 1 for our new method is given by the following equation. So the big C prime is the intersection of all the x satisfying the lambda less than the C prime alpha prime. However, the traditional test has the critical region big C is defined as the following equation, where we denote by the C alpha the critical value for the traditional composite versus the composite likelihood ratio test satisfying this equation. The main difference, traditional hypothesis tests reject H null if the observed sample X belongs to the intersection of all sets, where the simple versus composite likelihood ratio test statistic lambda is less than a constant critical value. Our new test rejects H null if the observed sample belongs to the intersection of all sets where the lambda is less than critical value C prime alpha prime that depends on the theta zero. Can they be equivalent? Yes. Consider the symptotic approximation as the sample size n tends to infinity. We have the following two conversions. So if the C prime alpha prime doesn't depend on the little theta zero, then the big C equals the big C prime, provided that the little c prime alpha prime equals the little c alpha. That is, the traditional test method and the new method are equivalent. We have this proposition give us the equation 1 that we can use it to calculate the alpha prime. So we summarize our new method. The modified significance level alpha prime for the new method should be greater than or equal to the original alpha if D0 greater than or equal to 1. The proposition suggests the following testing procedure for a finite sample X of size n. For a test with significance level alpha, with the original null hypothesis is little theta in the big theta 0, and H1 is little theta in the big theta 1. First step, we let alpha prime be as in the equation 1 described in the proposition. Step 2, for each little theta 0 in the big theta 0, we reject the simple null hypothesis little theta equal to the little theta 0 in favor of the alternative little theta in the big theta 1 if the p-value less than the alpha prime. Last step, we reject the original null hypothesis if the simple null hypothesis is rejected for every little theta 0 in the big theta 0. We can also use our method to construct confidence intervals. There are a variety of approaches to eliminating the nuisance parameter for inference for theta. But again, there are challenges such as the difficulty in finding a statistic y equal to ux whose distribution depends on theta but not on phi. So the traditional LRT method is described at this page. So the confidence region can be found by the equation 2. There are situations where the supremum of the likelihood over phi is not analytically tractable, and thus finding the critical value C alpha is difficult. Our new method, introduced in the section 2, allow a different approach. So we construct the confidence region by the equation 3. Let's use an example to compare our method with the traditional methods. So in the case where the joint supremum of likelihood and the critical value C prime alpha prime can be readily found. The example says, consider a simple linear regression. yi equals theta phi xi plus theta phi squared plus epsilon I, where the theta and phi are unknown parameters and epsilon I are the independent and identically distributed Gaussian noise with zero mean. Suppose that the focus is on the parameter theta. We want to estimate theta so that the phi is considered a nuisance parameter. The joint maximum likelihood estimator for theta and phi can be estimated via the ordinary least squares method. The likelihood ratio test for the H null, theta equal to theta 0, phi equal to phi 0 versus H1 not theta 0, not H null can be carried out using the standard F statistic. Thus, a confidence interval for theta can be constructed using our proposed method via equation 3. In contrast, for given theta 0, finding the MLE for phi requires solving a quadratic equation, and the distribution of the constrained maximum supremum of the likelihood over supremum of the likelihood is analytically intractable. Therefore, a confidence interval is not obtainable using the traditional LRT framework as described in the equation 2. To compare the performance of our new method with the traditional method, we conducted a simulation designed as the following. So for each sample size, we generate data with the linear regression model, and then we construct the confidence intervals by both the new method and the traditional method. And then we calculate the proportion of times that little theta 0 in the interval for both methods. Figure 1 shows the result. The blue line shows the traditional method. The red line shows our new method. It's noticeable that for small sample size like n equals 5 or 15, our method is noticeably better than the traditional method. So the proportion of times that our confidence interval contains the true parameter is closer to 95%. And as n increase, both methods are close to the 95%. Both methods give us the proportion close to 95%. We also studied the rejection rate of the hypothesis test by comparing our new method with the traditional LRT. Figure 2 shows the result. Again, the blue line shows the traditional method and the red line shows our new method. So especially for small sample size, our method is better. And as the sample size grow larger, and both methods give us the desired 0.05, which is about the risk of type 1 error. By comparing the powers, we got the idea that our method not always give us the larger power. But we know that a larger power doesn't mean it is better. If the test has always a high power, means the test is too aggressive. So we look at the true values of theta. When theta is 1, that's the true value of theta. And the true value of the alternative phi, which is the phi equals 2. So if you look at here, our method, the red line, shows the power is close to 0.05, which is desired. So for the parameters close to the true values, the power should be close to the risk of type 1 error or the alpha level. At the end, we compared the distribution of the highest p-values and the theoretical distribution described in our proposition. We see the overlay of the histograms show us no big difference. Typically, they are the same distribution. We explored some other applications as well, like some higher dimensional method with our new method. So for example, we calculated the alpha prime by this equation, and we also studied that when the d0 equals d1, what will be the alpha prime. So we explore the result with the example 2. Consider a two-dimensional case. We test the null hypothesis is theta within a disk, and the alternative is outside of that disk. The figure 5 shows us the rejection rate across different sample sizes. You see that as the sample size is efficiently large, that the rejection rate is close to 0.05, means our method works for the two-dimensional case or higher dimensional case. So here's my references, and thank you.